Hi, this video is on modular exponentiation, which is the problem of computing a to the e in z sub n. And we're interested in particular in the cases where a is huge. A and n are both huge. A is smaller than n, but it's still huge, and e can be arbitrarily large. And in general, this looks like an insanely difficult thing to do. So it looks horrible. And so it's one of the most spectacular use of the divide and conquer technique. So if you, let's say we want to compute a to the, just to be definite, 257th. So in z sub n for some a and some n. You might think, well, just take a, multiply it by itself to get a squared, and then multiply that by a to get a cubed. So we might think of a chart where we have a to the 1, a to the 2, a to the 3, a to the 4, a to the 257. So depending on how big, if a is huge, this, first of all, if a is huge, by the time we get up to a, 257 a's multiplied together, it'll be an insanely large number. So it's really important. This problem is not even relevant or interesting unless we're reducing all of these in z sub n. So in this case, as every time you compute a times another, so when we do a times a, we drop it back. So all the numbers are less than n in this chart. So things never get completely crazy. So n could be 300 digits, but none of these numbers would ever get more than 300 digits. They're all less than n. So that's one interesting fact that we need. But the other one is, this is just silly. And the reason it's silly is if you want to get up to a to the 257, so I accidentally rigged this, that's actually a to the 256 times 1, a to the 1. So we could just compute a to the 1 and then square it to get a squared, and then square it again to get a squared squared, which is a to the 4th, and then square that to get a to the 8th. And so after not that many, we'll have a to the 256, and then we can multiply by a, and we'll be done. So the squaring reduces it. So the a to the e, the stupid way, would be in theta of e. So the successive squaring, that algorithm is in theta of log base 2 of e. So it's our usual divide and conquer thing. So there's some details to be worked out, but that's essentially all there is to modular exponentiation. So let's look at some of the details. All right, so let's do an example, and that'll pretty much be all we need to say. There is some code called modExp in the course website, modexp.java, that you can run. So anytime you're working on these things and aren't sure what's going on or if you're doing the right thing, on the routine exercise, for example, you can run that program to see like the total slicked up algorithm. So let's say we want to do 73 to the 29th. So the basic idea is all we need is the powers of 2. So if we could just express 29 as powers in binary, then we could say, well, this is 73, but let's remember how we express 29 in binary. The smart thing to do is, since the 29 itself is odd, that implies that the last bit, rightmost bit, is 1. So in binary, that means the binary value is going to have a 1 in the last bit. So 29 in binary is equal to a 1 over here in the far right. Okay, and then the technique, if you remember from your CS 1400, is you divide by 2. Now this number is even, so that says the next bit, the 2's bit, is 0. So we don't multiply by 73 to the 2 because it's simply not there in the binary. Okay, and then we do 7, so that's odd. So this guy is 1, so we do want to multiply by 73 to the 4th. And the next one is divide by 2 again, that's odd. So that means this is a 1, and we multiply by 73 to the 8th. And then divide by 2 again. These dividing by 2s are all, of course, integer division, so that's also odd. So that makes this bit 1, and this bit, and then so we have 73 to the 16th. And you can check that this works if you've forgotten that 16 plus 8 is 24, plus 4 is 28, plus 1 is 29. So this column here is just the standard CS 1400 algorithm for converting a decimal value 29 into binary, where you just, the odd and evens, the bits are just you can just read off from these numbers. So that's part of the slicked up algorithm. So let's look at it. So we start off here and we have 73 to the 1, so that's the first value. And if we want, we can write some numbers off the left, but I'm not even going to bother. So and then next to that we write 29. Okay. And below that, now we do 73 squared. So I'm going to do this off the side to keep my chart neat. So 73 squared is, I'm going to have to pull out a calculator here, which you won't be able to see. So I take 73 times 73, and this is explained in the rsa.pdf very carefully. So that's 5329. Oops. But we need it in Z sub, what are we doing? I've forgotten. Z sub 151. So what we do is we divide 5329 by 151, and we get 35 point something, 35.29139. So in the in Z151, the 35 is 0 because it's 35 times 151. So what we can do in the calculator is very conveniently subtract 35 and hit equals, just get the decimal part, the 0.2, and then times it by 151. So when I do that, I get 43.9999, which obviously is trying its hardest to be 44. If you don't believe me, that's that 35 times 151 is 5285 plus 44. So that is the remainder. So we got the 35 times the n number plus 44. So is that right? 53, 20, 29, yep. Okay, so the point is, in this column, the next number down is just 44. And we remember, we don't have to write these down because it's a waste of time, but that's what these are. And the next one is going to be 73 to the 4th. So this column is kind of optional. It's good to do on the test or whatever if you're trying to really understand what's going on. Okay, and then in this column, just to keep track, we write down the division. And now what do? We take 44 and square it and reduce it. So 44 squared is 1936. So I divide that by 151. That's, whoops. So what did I say? 44 squared is 1936 divided by 151 equals, so it's 12 point something. So I subtract the 12 equals, so I get 0.82119, multiply that by 151, and I get 123.9999, so it's 124. And then 73 to the 8th will be, so I take 124 and square it, 15,376, divide that by 151, it's 101 point something, so I subtract the 101, I get 0.827, and times it by 151, I get 125. So that's, I just want to check quickly. No, I guess I won't. We'll just have to hope I'm doing things right, like always. So finally, 74 to the 16th will be 125 squared is 15,625 divided by 151 is 103 point something, so subtract the 103 and get 0.47 times 151 is 72. Okay, so now you simply, and we stop here in this column when we hit 1 because the next thing down is 0, which means we're done. So in binary, we just circle the odd ones. That's all you have to do. So it's 73, so odd, 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 odd. So we have to multiply all 4 of these together. And a convenient way to do that is to keep a cumulative total. So that's an odd one. And then when I see this odd one, I multiply 73 times 124. So let's do that. So 73 times 124 is 9052. Reduce that mod 151, so I divide by 151, subtract 59, multiply by 151, and you get 143. And then the next odd one, we multiply 125 times the cumulative thing. So 143 times 125 is 17,875, divide by 151, subtract 118, multiply by 151, I get 57. And the last one is this odd number times, so 72 times 57, the cumulative thing times the last one, 4104, minus 27 times 151, turns out to be 27. So that's our final answer. And that may or may not be correct, depending on whether I did the arithmetic right on my speedy calculator work, but that's the algorithm for modular exponentiation, and that's really all there is to it. So when you run the program, here I'm going to turn for a moment to it. So on the course website, I'm looking in the code folder, and it doesn't have it because I haven't put it here yet. All right, so I'm going to have to go somewhere else. Hang on a sec. Okay, so I've put the code you need for the RSA. It's in a folder named RSA in the code folder in the course website. So it's in the course website / using Unix notation code / RSA, and in there's a folder called a file named modexp.java. So if you just run that, compile and run it, it asks you for A, E, and N, and in fact I can verify that amazingly I didn't make any mistakes in doing those steps. So I'm getting pretty good at reducing things mod 151 in this example on the calculator. You may have a calculator fancy enough to do the mod operation, which is great, I guess, but I don't. So of course in a program, if you look at this program, of course it uses the big integer, a lot of big integer methods, and uses the mod operator, which takes care of it for us. Okay, so that's the end of the video on modular exponentiation. So the next video is on the greatest common divisor and getting those magical coefficients to decrypt the RSA messages. So thanks for listening.